Oh yeah, well, old enough to remember stuff now that didn't even happen. So, thank you, Richard. This is another one that I've never done before, so we're sort of plowing new ground here. I hardly have any old slides in it this time, not even recycled. I had to do them all from scratch. As Richard already mentioned, the Lagrangian points are things that apply to gravitational systems where one body orbits around another, such as the moon around the earth or the earth around the sun. And whenever we have a situation like that, there are certain points, and he mentioned there are 5 of them, in the orbit of the smaller body around the larger one, where all the forces cancel out essentially. We'll get a little more detail on that in a minute. And objects can be placed there, small objects that are negligible in mass compared to the either the sun and earth or earth and moon, such as little rocks or satellites or something like that, that are stable, and they will orbit around the larger body at the same speed that the smaller body does, and they all move together. So it's kind of counterintuitive if you're thinking of Kepler's laws, and we'll see how that works after a little while as well. Here are the 5 Lagrangian points and the lines of equal potential. In this case, we're showing the sun and the earth. The moon is not shown. These 2 green dots here are the first and second Lagrangian points. The moon is not shown in this diagram. And the first 2 and the third one on the opposite side are called the collinear points because they're all in a straight line with the 2 bodies. L1, as you can see, is inside the orbit of the smaller body. L2 is outside. And 3 is diametrically opposite. 4 and 5 are called the triangular Lagrangian points because the first body to that point down to the second one forms an equilateral triangle, and likewise this way. From here to here to here around is another equilateral triangle. So those are called the triangular points. The forces of equipotential here show where the gravity and the centrifugal force cancel out, and objects would have a stable orbit at this point and here and here and here and here. Now, before any physicists get their hackles up about the term centrifugal force and tell me there is no such thing, I will concede that you're right. Centrifugal force is a term that's used to explain what is seen and felt, even though physicists will tell you that it's really not a force, it's a resultant from 2 other forces, the vectors of gravity forming the centripetal force, pulling on the second object and making it attracted towards the first one, and the momentum of the forward motion. If you take those 2 vectors and add them together, the resultant is what moves the object around in orbit. So to use an example, if you tie a rock on a string and whirl the rock around on the end of the string, the centripetal force, or the force towards the center, is provided by the string, and the momentum causes it to orbit around you if you're swinging it around. However, if you were an ant sitting on that rock, at all times you would feel a force directly away from the person swinging the string around on the rock, and that felt force, whether it's a resultant vector or whether it's a true force, is commonly referred to as centrifugal force, and it's used in common objects such as centrifuges and rides at the fairgrounds and so on. It's a real phenomenon whether the centrifugal force is the correct term for it or not. We will use that, I will use that this evening, because it's certainly a useful way to describe what's going on. The L4 and L5 points are, as you can see, the high points of the potential, yet they're the most stable. You can, it's counterintuitive, but you can sort of think of it as like a plateau on the top of a mountain with a dished out area. So if you put something right there, it will not leave that point. In fact, if you displace it a little bit, it'll head right back to it. So those points are the most stable, and if you doubt, we'll look into the example of the Trojan asteroids later on, and that gives proof of the fact that those are stable Lagrangian points. A little bit about the history of this. 1769, so this has been around a good while, even before we were in school. And Leonhard Euler, who's primarily known for mathematical work, discovered the three collinear ones. Remember, the ones that are in a straight line between the two bodies, one on the far side and then on the near side, one towards the central object and the one away from it. He discovered those in 1769. 3 years later, Joseph Louis Lagrange discovered all five of them and published this in his essay on the three-body problem. And he was the first one to discover the triangular points L4 and L5. Incidentally, regarding pronunciation, the Frenchman himself, who was of Italian origin but worked in France, pronounced his name Lagrange, but it sounds fakey and weird to talk about the Lagrangian point. So now that that's an English word, I'm just going to call it Lagrangian. Otherwise, it'd be garbage. So for this to work, Lagrange worked out the idea that if mass 1 is at least 24.96 times as massive as mass 2, and that's, of course, easily accomplished with the Sun relative to the Earth, and actually it's still in effect with the Earth with respect to the Moon, then you will have these 5 Lagrangian points at which negligible masses, like little asteroids or satellites, can orbit around the central mass in the same time period as the mass 2 orbits around. Not necessarily in the same spot, but with the same orbital speed and year. So that's a little bit weird. It's not like what we were talking about last time. Here's the 5 points again shown in this diagram, which I might be able to get to work. Here's, for example, the Sun and the Earth. The first and second points are exaggerated in their difference in distance from the second mass here. If the larger this is compared to that, the closer those distances get together. And even with the Earth and Moon, which are not nearly as different as the Sun and the Earth, they're still just a few miles different. But if you had masses that were very close together, like a binary star, for example, then these points would be greatly different in their distance from the second object. And of course, here's our equilateral triangle. Another way to look at all of this is if you have a fixed frame of reference, you have all these vectors and everything with resultants. If you have a rotating frame of reference, you don't have to do that. If you're the ant on the rock getting spun around, you're moving with a rotating frame of reference, and you don't have to consider the vectors, because the only one that affects you is like straight out from the center. If I can get this to work, it's not essential that I do, but let's just see what happens here. If I take supposedly in here there it is. I copy that and I put it into the browser, which isn't even here. Forget it. The
browser?
Yeah?
It's the fourth from the top left.
Oh, okay. Okay, Internet Explorer. Okay. Let's see if that will do anything. Yeah, there it goes. There's the rotating frame of reference, which looks truly weird, doesn't it? You wouldn't expect any sort of model of something going on in the solar system to be tied together like that. But that's the way the Lagrangian points work. If you have the sun there and the earth there, then the 5 Lagrangian points move around at the same speed around the sun, the same orbital velocity that the earth does. So it is all tied together. Now, let's see if I can get back out of that and back up to, is that it? See where?
Go to the taskbar. Go for that.
For here?
Down. To the right now.
Oh, there. Okay. And then back to the full
F5.
F5.
Oh, is that right?
That's all right. We'll just move it right along. Something told me not to even try that, but I didn't listen to myself. There we go. Here's a little different version of the same thing with a little more detail, and this one isn't supposed to move, so we're okay on that. Again, we have a general system, but it certainly looks like the sun and earth to me. L1 is in closer, L2 is farther away, L3 is on the opposite side, 4 and 5 lead and follow the earth in its orbit around the sun at a 60-degree angle all the way around. And this only is true if this body is at least 25 times as big as that one, or massive. Okay, notice that at least the 3, you can see it, but also the 4 and 5 look like they're on the same path as the earth, but they're actually a little bit outside it. And we'll get to that after a little bit to see why that's the case. They follow at the same speed, but they're not exactly on the same track as the earth. Here's another way of looking at it on kind of one of those deals where you take a rubber sheet with weights in different spots on it and show the warping of the space-time continuum and the gravitational effects like that. This is kind of a little different way where you see the huge gravitational effect of the sun making that potential well, and the earth out here farther, and then the 2 Lagrangian points on either side of the earth and on the opposite side of the sun, and then the leading and following where we have all the forces canceling out. We're going to take each one of these in turn and explain why they are Lagrangian points. L1 lies on this line through the 2 points, but on the inside. And it says it's the most intuitively understood. I'm not sure that 1 and 2 are really any different in that regard. Okay, what happens here is the mystery we have to explain is why L1 is like an earth, a little bitty tiny earth, closer to the sun than the earth actually is, yet it has the same orbital period as the earth does. That is counterintuitive. And while we're at it, L2 is farther away, but it moves around together. As you saw on that animated slide, everything's like it's bolted together. The reason is that at this point, the L1 point, part of the sun's gravitational pull on that L1 point is canceled out by the earth pulling in the opposite direction. It's almost as if the sun didn't have as strong a gravitational pull as it normally does, because the earth's pulling on it from the back side. And it's like that planet is orbiting around a less massive star, which even though it's closer, which would make it go faster, the less mass from the sun would make it go slower. So you're partly canceling out the mass of the sun by the earth pulling on it from behind. So that's why that is a Lagrangian point there. Remember from last time, Kepler's third law was that the period, or the year of a planet in Earth years squared, is equal to its distance from the sun in astronomical units cubed. In other words, the farther a planet is from the sun, the longer it takes it to go around the sun. And as we just saw, at those L1 and L2 points, that seems to defy that, because 1 is closer to the sun, it's got a smaller d, yet the p is the same. And L2 is farther away from the sun, so it should have a longer year, but it doesn't. And we'll get into that one in a little more in a moment as well. Now, this kind of leads into it a little bit when Newton derived Kepler's law. Remember how this worked. Tycho Brahe made all of the measurements very accurately for his time of the planets, especially Mars, and had all these tables of data. Kepler analyzed the tables of data and came up with his 3 laws of motion that would exactly predict where a planet would be. And later on, Newton analyzed Kepler's laws and Tycho's data and found that once he explained the force of gravity and how it worked, the inverse square, all of this fell into place. And when he re-derived Kepler's laws from scratch, not just from data, but from thinking about the effect of gravity on objects, this is what he came up with. Here's like the mass of the sun plus the mass of the planet times the year squared equals, now this is the distance of the sun from its barycenter. Remember, the Earth and sun, the Earth doesn't really rotate around the sun. The Earth revolves around a point that's between the center of the sun and the center of the Earth. It's still inside the sun, but the Earth or the sun kind of ooches back and forth just a little bit as the Earth swings around it. The distance of the sun from that point, which Newton realized had to be in the equation, is that. Here's the thing we mainly think of, that's the distance of the planet from the barycenter, which is almost the same as the distance of the planet from the sun, since the barycenter is still inside the sun. Now, for a very light planet that's fairly far from the sun, such as Mars, the mass of the planet is negligible compared to the mass of the sun. So you can cancel that out and just have the mass of the sun there on this side. And in solar masses, that's 1. So the left side becomes p squared. On the right side, Mars doesn't swing the sun around that much, so the barycenter is almost at the center of the sun. So you can drop that term, and then you have the distance of the planet from the sun cubed. In other words, for that simple condition, Newton's carefully derived law just reverts to Kepler's 3rd law of p squared equals d cubed. So those are the factors that go into the calculations for the Lagrangian points. Now, I've already said this, I think. An object that orbits the sun more closely than the Earth, something like at L1 point, should have a shorter orbital period than the Earth. But that ignores the effect of the Earth pulling on it from the back side. So once you get it directly in between the Earth and the sun at just the right distance, the Earth's gravity weakens the force from the sun and therefore increases the orbital period, just as if the sun were less massive than it actually is. Does that make sense? Okay. And the closer to the Earth the object is, the greater that effect is. You know, if you start at L1 and start moving closer and closer to the Earth has more and more effect over it than the sun does. And if you go about 2/3 of the way in, that's where the moon is. Well, what does the moon do? It just goes ahead and orbits around the Earth. So if you get it really close to the Earth, it orbits around the Earth. But if it's about 3 to 4 times as far away as the moon is, then it's got an effect on the sun. That's the main effect that it feels. What if you get it even closer to the sun, away from the Earth? Well, then it's just like another planet, like Venus. That would meet that. It orbits around the sun. So close to the Earth goes around the Earth. Close to the sun goes around the sun. But at just the right point, all of those forces balance, and it moves around the sun with the Earth in the same position all the time. Okay, does that make sense? Any question about the L1?
Think about those.
Yeah, you do. Yes. Okay, here's if you'd rather have equations than words, here it is. This sets up the balance between the gravitational force and the centrifugal force. And if you set those equal to each other, the little r is the distance of the Lagrangian point from the second body. So if you solve for that, this would be a booger of an equation to solve. If you tried to solve it, you wind up using a quintic equation, which can be done, especially with iterative methods and modern computers.
What kind of equation?
Quintic, a fifth power. Not a linear, not quadratic, not cubic, but on to fifth order equation. So you don't want to do that, but if you make the assumption that M2 is much more or is much less massive than M1, like the Earth compared to the moon, Sun, or the Moon compared to the Earth, and in that case it gets a whole lot simpler, which we always like to see. And it says approximately equal, but it's within a couple of miles of being exactly right. I check this out, if we substitute here the mass of the Sun and here the mass of the Earth and do the arithmetic on it, we find that L1 is about 933,000 miles from the Earth. And although this is for L1, that means 933,000 miles towards the Sun, right? It's also almost exactly the same thing as L2 on the other side. Now notice that that's bigger than the moon's orbit, isn't it? About 240,000 miles. So this is like 3.7 times the distance to the moon. So it's well outside the moon's orbit, which we've already figured up intuitively because the moon just goes ahead and orbits around the Earth, and stuff at the Lagrangian points don't. Okay, here's some uses of the different Lagrangian points. The L1 point is a good spot for making observations of the Sun-Earth system, because whatever satellite you put there is never in the Earth's shadow or the moon's shadow, because it's outside the orbit of the moon and it's on the sun side of that. So it's always in direct sunlight, and it's always got a clear shot of the Earth. And we have, here's one satellite mission that was used to do just that. After it was calculated by Robert W. Farquhar, an astrodynamicist who showed that you could actually put satellites in those spots. That was the beginning of all of the Lagrangian missions, was when those calculations were made. Pretty good PhD thesis. And SOHO, which everybody knows about, the Solar and Heliospheric Observatory, that's at L1 also. It mentions the term halo orbit. If you put something that's not exactly at L1 but close to it, it will circle around that point where L1 is. They call that an orbit, but strictly speaking it isn't an orbit, is it? Because an orbit is around some body and there's nothing there. It's a point, but it's so stable that it will circle around the point like something about to go down the drain, you know. And if you put it right at the L1 point, it would be stationary, but close to it, it will just circle around it. So that's the, and then there are Lissajous orbits as well, which get more complicated with kind of a figure-8 sweeping pattern. Kind of like if you have a floppy telescope mount and you're looking at a star and you tap the end of the telescope tube and the star is jumping all around. That's a Lissajous pattern, and that's the kind of orbit that you have for the Advanced Composition Explorer. The Earth-Moon L1. Remember, this is really close to the Earth because the Earth-Sun L1 is 4 times as far away as the Moon. So this is within the Earth-Moon system, and since the Earth and Moon are more comparable in mass than the Sun and the Earth, that L1 is pretty far inside that lunar orbit. In fact, it's pretty much at the halfway point between the Earth and the Moon. So that would be a good place to have a halfway manned space station where you could get to that point, and would always be directly in line with the Moon. You wouldn't have to wait for something to come into the right spot. It would always be sitting there just halfway between the Earth and the Moon. In a binary star system like we were talking about last time, where one star expands and overflows and pours its material onto a companion star like a white dwarf. The point at the apex of that point where say the red giant's material is funneling over towards the white dwarf, well, let's just go ahead and look at it. I have no idea what language that is, maybe Chinese or Korean or something. I don't know what that is, but I can tell you what it's got to say. And this is the red giant star. They've got Roche spelled out there. This is the Roche lobe. That point is the L1 Lagrangian point, and here's the white dwarf star. And here's the kind of an artist's conception of all of that going on. Remember last time we had the type 1a supernovae where the red giant piles its outer surface layers onto the white dwarf until it exceeds the Chandrasekhar limit, and then it explodes as a supernova. It goes through that L1 Lagrangian point on the way over to the other star. Okay, good spot for research satellites as well. We've got Sun over here, here's the Earth, and here's the L1 point. This one actually shows the Moon in its orbit around the Earth here. And there's the L1 Sun-Earth Lagrangian point, and there's the little satellite, the ACE, or Advanced Composition Explorer. And we'll hear more about that later on, I'm sure. But it's in a halo orbit around that L1 point. L2 point. These go faster as we go because whatever we get from the first ones applies to additional ones. The L2 point is also a collinear point along this same line, but this time it's outside. And again, the gravitational forces combine to balance the centrifugal effect, and we wind up with a anti-Kepler thing again. This time, L2 being farther from the sun, you would expect it to go around the sun slower, wouldn't you, like Mars does. But it's so close to the Earth that the Earth's gravity adds to that of the sun, and the effect is though the sun is more massive, and that makes it go into a faster orbit even though it's farther away. And at just the right point, it balances out and moves at exactly the same angular velocity as the Earth does around the sun, so it just follows it right around on that outside corner. Here's the L2 point again, and this is good because it shows here's the sun and Earth, the L1's in here somewhere, L2's out here, and here's the Moon's orbit, which we can see is only about a third of the way out to where the L2 point is with that little X there. So the Moon's orbit is well within the Lagrangian system of the Earth-Moon. Okay, here's the equation to solve it, and if this looks familiar, it's because it's exactly the same once we make the assumption of the greater mass for M2 or M1 than M2, then it works out the same. So the distance is the same, the 933,000 miles outside the Earth's orbit as opposed to inside. So they're pretty much within a few miles of being exactly the same. L2 is a good spot for space-based observatories because it's on the far side of the sun, and it's always in the same position with respect to the sun and Earth. It's like where the full moon is, except all the time when it's at that distance. And so you don't have to keep recalibrating it and shielding it as it moves around with respect to the Earth and sun and moon. The only slight problem is it's beyond the reach of the Earth's umbra. How far does the umbra reach out? Remember, if you've watched lunar eclipses, and judging by the curvature of the Earth's shadow on the moon, the Earth's shadow is about 3 times the diameter of the moon at the moon's distance. So when the moon's moving through the Earth's shadow, it goes across 3 moon diameters as it's doing that. If we went out 3 times as far, it would be down to a point, wouldn't it? But this is 3.7 times as far, so it's beyond the point where there is any umbra at all. So what would the Earth-Sun system look like from the L2 point? It'd look like an annular eclipse, wouldn't it? With the Earth not quite blocking out the whole sun, with a little ring of sunlight around the Earth all the time. But you can calibrate for that and adjust to it. and so that's a good place for observatories. The Herschel and Planck observatories are already there, and this Chang'e 2, I don't know about that, but I hope to learn more about it later on this evening. And the Wilkinson microwave anisotropy probe was there until October 2010. So those are good places for observatories there on the far Lagrangian point. And the Gaia probe and the Webb Space Telescope are supposed to be placed at that Sun-Earth L2. That one this October, and this one who knows when, since it's a NASA project. The Earth-Moon L2 would be a good location for a communications satellite if we covering the moon's far side. Now, why would we need that? If we ever had people on the moon on the far side, you can't send a radio signal from that through the moon to the Earth. You need some kind of a satellite up above that, and that would the L2 point on the far side of the moon would be good for that. And it's also suggested that it'd be a good place for a propellant depot as part of space exploration and so on. Probably not both at the same time. I think you probably wouldn't want both of those in the same spot. Okay, L3 point on the far side. It's again on this collinear line there, but on the opposite side, the far side of the sun, a little bit outside the Earth's orbit, but slightly closer to the sun than the Earth is. Now, at first that sounds like a contradiction, doesn't it? It's outside the dotted line, but it's closer to the sun than the Earth is. That's because this drawing isn't exactly accurate. If the drawing with the dotted lines represents the Earth's orbit, the sun is not right in the middle of it, is it? It's over this way a little bit because it's the barycenter that should be at the center of the diagram. That's the center of the Earth's orbit, is the barycenter, center of gravity or center of mass. That pushes the sun a little farther to the left, and since the L3 point depends on the mass of the sun, it's going to be outside that a little bit as well. So everything is shifted to the left a little bit by the fact that the barycenter and the true center of the Earth's orbit are not the same thing. Solving this equation...
Go back to that one.
Okay, yeah. This is one that I had to draw out.
I have to think about it. It's a little outside the Earth's orbit, but then it's closer.
Right, because the sun is over here farther while the Earth is still on the dotted line.
Because you're using the barycenter as a reference point.
Right, yes.
Okay, right.
Yep. Yeah, that's one you have to think about.
Think about that.
If you want to. You know, not 99.9% of the people in the world have never thought about this and are none the worse for it. But we're weird, so that's what we do. Okay, same equation again. We put in the different distances and things. This time we get a different solution, and that puts it right where it is on the far side of the sun. Here was where the counter-Earth was in science fiction. You know, the thought being that if there was another planet, just like the Earth, but on the L3 point, on the opposite side of the sun would be in the way and you would never see it. You could have another whole Earth over there that we wouldn't know about. Well, that's kind of shot down from several angles. One is we've had probes go all through the solar system and it's not there. So that's the number one piece of evidence that it's not there, is that it's just not there. Also, that point is unstable, and because the other planets come so close to it. Venus is within 0.27 astronomical units every year and a half or so, as we saw last month, and that would pull it out of its orbit and destabilize that point. Also, is that on this slide or the next one? Yeah, there's how Venus would be coming that close to either the Earth or the counter-Earth, depending on what was supposed to be there, and if it was that Lagrangian point, it would totally disrupt it.
Some people call it Vulcan.
I thought Vulcan was the one inside of Mercury,
Maybe
the extra hot vulcanized. No, yeah.
Yes.
Yeah. Okay, here's the other thing is the Earth's orbit is elliptical. So sometimes it goes faster and sometimes it goes slower. When the Earth would be going the fastest, the L3 would be going the slowest, and they'd both wind up on the same side of the sun. And then when the Earth was at the closest point to the sun, it would be going the fastest, and the L3 would be going the slowest, and be winding up on the same side of the sun again, all of the opposite sides. So you should be able to see it then. And if that weren't enough, the Jupiter Sun barycenter is outside the sun. Jupiter is so massive that the sun really swings around because of that, and it just gets out of the way enough, even if the Earth's orbit weren't eccentric, for us to see it. It's sort of like if you're swinging a little kid around at arm's length. You have to lean over backwards a little bit to do that, to maintain your balance. If you're swinging me around, you'd probably have to run around in a circle in order to not fall down. And that's what we're talking about here. With Jupiter and the sun, the barycenter is outside the sun, so it moves back and forth a great deal because of that. And at certain times, when it's at right angles to us, we should be able to easily see this counter Earth. But it's not there anyhow. A spacecraft near there, that would be a good spot to take a look at the sun and see what it's up to before that side faces us, wouldn't it? If we had something over there at the L3 point, we could see a sunspot group forming or nasty flares looking like they're getting ready to act up, and give us a 2-week warning before that side faced around towards the Earth. And so it'd be good for making space weather forecasts, and which you would need for manned missions and things like that. Changing the subject here, which is what that means, the Sun-Jupiter L3 point is where the Hilda family of asteroids is, on the opposite side of the sun from Jupiter. We'll see a picture of that later. 4 and 5, those are at the corners of the equilateral triangles leading and following the sun or rather the Earth in its orbit around the sun. Again, the forces all cancel out, and we see why. Here, they're already the same distance between, let's just say that's the sun and the Earth. The L4 point is the same distance from the sun as it is from the Earth. That means that the inverse square law kind of cancels out there because the distances are the same, so the forces are the only thing that's different. The sun is proportional, it's got a pull proportional to its mass. The Earth is pulling on L4 proportional to its mass. Let's back up there for a second and see. So the sun is pulling this way, the Earth is pulling this way on it at a force proportional. The sun, of course, being more massive than the Earth, has a greater pull. And the acceleration is, of course, in the counterclockwise direction, because the sun is ahead of where the Earth is, and the Earth, the L4 is, and the Earth is behind it. So the sun is accelerating that point around it. But remember, the fixed frame of reference, or excuse me, the rotating frame of reference motion slide that we saw earlier, all of that moves together because the acceleration is in that curved path, just like the Earth itself. But here, this point is being accelerated this way by the sun, pulled backwards some by the Earth, and it exactly balances out so that the distance doesn't change any. If it got a little farther ahead, the resultant would be stronger this way. If it got a little farther behind, it would be stronger this way. So it keeps it in that same spot. Believe I already said that. This was discovered by Lagrange himself when he was writing that paper on the three-body problem. Here's a satellite at the L4 position of the Earth-Moon system. Here we get to see the barycenter in effect. This inner line is the Moon's orbit around the Earth, and we can clearly see that L4 is outside that because the distance from the barycenter is the same. If this is supposed to be the Earth, and the barycenter of the Moon-Earth system is pretty far off to the side compared to how the Earth-Sun one is. And so the offset here is about the same as the offset between the true center of the Earth and the barycenter of the Earth-Moon system. So everything's just shifted outside by that amount. They could have done a little better job drawing the continents in, I think. That's kind of like a shoe, a sole of a shoe or something. The L4 and L5, I'm not going to do 5 because it's exactly the same as 4. So you get a bonus on that. They're called the triangular Lagrange points, or the Trojan points, because the asteroids that lurk at those two spots were named after heroes in Homer's Iliad in the Siege of Troy. And they first started naming them at random for the Greek side or the Trojan side, but eventually they decided to call the ones ahead, the leading L4 ones, the Greek camp, and the following ones at L5 would be the Trojan camp. But there were still a couple that got mixed up. Here's all the asteroids, by the way. We always learn at the first level that the asteroid belt is between Mars and Jupiter. Well, that's certainly true for a lot of them. But here's the orbit of Jupiter, and here are the L4 ones, the Greek camp, and the L5 ones that follow in that point, the Trojan camp. And remember, the Hilda ones are on the far side of the L3 Sun-Jupiter system. This isn't showing up very well at all, is it? Can you see that at all?
With difficulty.
Okay, so this is a list of a number of, this isn't all of them by any means, but a list of the famous Greek heroes like Achilles, Nestor, Odysseus, the main one of all, who was involved with the Odyssey after the war. And then over on this side, Priam and Aeneas, Troilus, those are all the Trojans. But for some reason, Patroclus was named in the Trojan camp, and Hector was named in the Greek camp. Maybe wrote the, yeah, right. Those were on the wrong side. So maybe that counted the Trojan horse expedition where they snuck in that way. But anyway, that's the way they're named now, after two wrong ones at least. Then since then they've all followed the Iliad. Other examples: the Sun, Earth, L4 and 5, 60 degrees ahead and behind the Sun. There's interplanetary dust there, little tiny planetoids at the L4 and L5 triangular points. And at least one asteroid, which was discovered just a couple of years ago and reported. So there's interplanetary dust and an asteroid at those points. Now, the Earth Moon L4 and L5, 60 degrees ahead and behind the Moon. There should be interplanetary dust in those spots as well, and in fact, they're even called the Kordylewski clouds. Unfortunately, they named something that's kind of turned out to not be there, because the Japanese Hiten spacecraft went through there a number of times and did not detect any increase in dust as it was going through there. So either the spacecraft was malfunctioning, although it seemed to work elsewhere, or there's no significant accumulation of dust at the Earth-Moon L4 and L5 points. Other examples: Neptune has at its 4 and 5 points, they're Trojan objects like little asteroids there. Saturn's moon Tethys has its own satellites. Tethys, of course, is a moon of Saturn, but it has two moons itself named Telesto and Calypso at its L4 and L5 points. So the moon's got moons. And Saturn's moon Dione has smaller moons Helene and Polydeuces at its L4 and L5. So we've got two moons of Saturn, each of which have two moons of their own at their own triangular Lagrangian points. And this last one I ought to just skip. The giant impact hypothesis said that there was this object named Theia that formed at the Sun-Earth 4 or 5 point and crashed into the Earth and formed the moon. You all know what I think of things like that, so we'll just skip over that. Then we get to a list of all of these missions Earth, Moon 4 and 5, L1, L1, on L2s, L1 and 2, L1, and those are the past and present missions, and then these were proposed missions, all of these Sun, Earth, or Earth, Moon at some point. And I got into that. I said, man, that would make a whole nother talk in itself someday. Well, today is the day, and after the break, Tim's going to be talking about that. Normally that would be the end of my talk right there, but it would set some kind of a record, so we can't do that. So here's my original idea about the cosmic distance ladder and the Lagrangian points. We saw that there was a missing rung in the cosmic distance ladder involving the Cepheid variables and RR Lyrae stars, because none of them are close enough to measure by the triangular parallax from the Earth's orbit. Here's the HR diagram, Hertzsprung-Russell diagram, showing the Cepheid variables and how they change in brightness and color as they fluctuate. And that's all compared to the sun right here. Blue giants up here, red dwarfs down there. Won't go into that anymore. Here it is on the evolutionary track. Remember, these are solar type stars that after they've lived for 10 billion years on the main sequence, turn into red giants and eject a planetary nebula, then go through this cycling unstable period, and then eventually wind up as a white dwarf star with a planetary nebula around it. So those are the Cepheid variables. Here's what their light curve looks like, as we saw last month. Sudden rise, gradual fall as the size and color changes. And fortunately, they're easy to find because you saw they were up near the top of the HR diagram, which means they're among the brightest stars in existence. So if you can see any individual stars in some other galaxy, they're probably Cepheid variables. There could well be. Periods vary from a few hours to 100 days, and as we'll see in the next slide, the relationship between the luminosity and the period. And once we use that, then we can go to ones that are farther away, where all we can measure is the period without measuring the distance at all, even estimating it. And once we do that, we can see what its true luminosity is compared to what it looks like in photographs and calculate the distance. We saw all about that last time. And here is our period luminosity diagram for the Cepheid variables of the type 1. There are two different types. This is the kind that are made up of stars in the outer spiral arms of spiral galaxies. Notice all the slop in the data. Incidentally, all the slop is in the vertical direction here, isn't it? Why do I say that? Because measuring the period is just as accurate as any stopwatch you've got. So that's not where the mistake is. The variability in the data points, the slop, is all in getting the true luminosity because we can't measure the distance that well. The heroes of the story were Henrietta Leavitt in 1911, measuring the distance to the smaller Magellanic Cloud, one of our satellite galaxies, with Cepheid variables. Harlow Shapley, a few years later, measured the distances to all of the globular clusters surrounding the Milky Way, and correctly assumed that since they were around the center of the galaxy, if he took the average distance to all the different globular clusters, he would see how far we were from the center of the Milky Way and get a pretty good idea of the size of our galaxy and where we were in it. So that was a major contribution. And then Hubble later on started measuring Cepheid variables using the biggest telescope in the world at the time, the 100-inch at Mount Wilson, Cepheids in other galaxies, and proved that they were so far away, like at least 1 million light years to the Andromeda galaxy, that they could not possibly be part of the Milky Way but were separate island universes. So that was a major breakthrough. But and then when it was discovered that there were two different kinds of Cepheid variables and they were using the wrong calibration curve for this, then overnight all the distances more than doubled, and now we know that Andromeda galaxy is more like 2.5 million light years away. So then there are Lyrae variables, which we'd also like to calibrate accurately. They're like the Cepheids. They have a gradual decline, sudden uptick, gradual decline, but right at the bottom there's a little bump, which makes them very easy to pick out from their light curves. They're almost as bright as the Cepheids, not quite, but they're still among the brightest stars in any galaxy that you look at. And here's the thing, you don't need a period luminosity curve for them because they're all the same luminosity. They all have the same absolute magnitude. So all you got to do is find one of those, and if your previous measurements and estimates of their distance have been correct, you can estimate the distance to whatever that RR Lyrae variable is in. And so for that reason, the Cepheids and RR Lyraes are called the yardsticks of the universe. From that, we can make a graph of the velocities of galaxies receding from us versus their distance and come up with a Hubble diagram. And again, lots of slop in there. This time the slop is in the horizontal direction because the velocity is easy to measure. Just spectroscopically, you look for the shift of a spectral line, and that's relatively easy to do. It's the distance that creates the uncertainty in this kind of diagram. And from the Hubble diagram, you can see we can determine the Hubble constant, the slope of the graph, and from the, that's it again in different units. And how we use it, we measure the speed of recession of a galaxy, read over to the line, assuming the line is truly there, which is the big assumption, and then read down to the distance, and that's the best way we have of estimating distance to really, really remote galaxies is by this. But it'd be nice to narrow down some of these distances. So those are some of the main things from last time. Here's an example. If we measure that a galaxy has a recession speed of 9,500 miles per second, we substitute that into the Hubble equation, and we can calculate that it's 700 million light years away, which is too far to measure by any kind of parallax or anything like that. So that's how we measure those big distances. Now here's the thing we started out with last time, the cosmic distance ladder. Here are the Cepheid variables, and here are the RR Lyrae variables. Here is what we can measure with parallax due to the Earth's orbit around the Sun. Before the Hubble, we had to stop here. With the Hubble and then the Hipparcos satellite, we were able to come out about that far with parallax measurements, which doesn't quite overlap with the RR Lyraes and doesn't overlap at all with the Cepheids. We can't get any of those measured accurately by parallax. And I don't need to do that, do I? You all know how this works. The farther something away is, the less parallax it has. The closer it is, the more it jumps back and forth. And a star that was 3.261 light years away has a parallax of 1 second. How many stars are that close to our solar system?
3.2?
Yeah, how many are that close?
Zero.
Zero. So everything is farther away from that, which means that every star you see in the sky has a parallax of less than 1 second. The Hipparcos could measure to 2 milliarc seconds, 0.002, and some of its observations were actually 001. So that's how it was able to extend our reach farther away. Just being above the turbulent atmosphere helps a lot, but it had some really nifty optics in it. So here's the plan here. This is Jupiter and the Sun. There's the L4 point in Jupiter's orbit, L5. What's the distance between those 2 points? Well, you might remember that Jupiter is 5.2 astronomical units from the Sun. We knew that long before we knew what an astronomical unit was. And let's just figure out what this distance is right here. This angle is 30 degrees, of course, because that's directly through the 2 equilateral triangles with 60-degree corners. Cosine of 30 degrees is the adjacent unknown x side over the hypotenuse, 5.2 astronomical units. So that distance right there is 4.50 astronomical units to the midline of the system. the whole distance between 4 and 5 is twice that, or right at exactly 9 astronomical units across that. Compare that to the baseline of the Earth's orbit, which is 2 astronomical units. So it's 4.5 times as wide a baseline if we use those to measure stellar parallaxes from. Now, how would we do that? Here's what I suggest be done. The European Space Agency should build 2 more Hipparcos satellites, or if the Gaia probes work out as expected, do 2 more of those. The Hipparcos mission ran from '89 to '93, and the Gaia one will be launched this October. European Space Agency. Hipparcos measured 1 million stars to within 2 milliarc seconds, and 100,000 of them were supposedly good to 1 milliarc second. That would give you a parallax distance of 1,600 light years limit, or for these 3,200 light years. So that on the cosmic distance ladder graph are the ones where it extended the farthest with that little annex onto the parallax measurement. Here's a little sad sidebar here. The reason I said European Space Agency is because this is no longer the mission of NASA. This, without comment, is the task given to the director, administrator of NASA by the president, and you don't see a lot about space exploration or Lagrangian points or anything in there. So whether you think this is a good idea or not, NASA is pretty much out of the picture as far as doing anything like this. Meanwhile, back to the European Space Agency. If we put 2 of those satellites at the 4 and 5 Lagrangian points in the Sun-Jupiter system, we'd have a 9 astronomical unit baseline that would allow parallax measurements 4.5 times as far as the original mission in the Earth orbit. And that would allow, just with the Hipparcos satellites, distances to 7,200 for the 2 milliarc seconds, or 14,000 light years for the if we had 1 milliarc second accuracy on some of the stars there. And supposedly the Gaia probe has higher resolution detectors and can measure 1/5 as much parallax as that, so 5 times the distance from that. The exact distance between the 2 satellites would be known at all times by the length of time it takes for a radio signal to go back and forth between them. And they would be made simultaneous. The measurements from one and the other could be made at exactly the same time, rather than waiting 6 months to go around to the opposite side of the Earth's orbit and then having to correct out proper motions of stars. This would be simultaneous measurements from the 2 different spots. And it could measure anything that way, but I would suggest the certain Cepheids and RR Lyrae variables would be the ones selected, because those are the ones we need to calibrate to measure distances to other galaxies. And if we took the 5 times limit on that, that would be 70,000 light years from this baseline with the Gaia type probe. So back to the diagram again. Here's what we had last time. This is with a Hipparcos satellite in the L4 and L5 positions with 2 milliarc second accuracy. Here's Hipparcos's again with 1 milliarc second, and then here's the Gaia one out to here. And you can see how much that overlaps with Cepheids and covers most of the RR Lyrae variables that are known. So, what do you all think about that? So that's it. Any questions on any of this? Yes?
So from the L4 to the L5 Jupiter, how much further parallax could we get? What was the exact number of light?
4.5 times as much as all the way across the Earth's orbit. That's 9 astronomical units compared to 2 for opposite sides of the Earth's orbit. So we got a 4.5 times bigger baseline, and measure 4.5 times farther with the same satellites, or with one that measures 5 times as accurately, then we get 5 times farther than that. Okay, anybody else? Yeah.
If you got two independent satellites,
Mhm.
how do you keep zero? I mean, you got to find a way to have a zero, right? A zero angle.
Well, they do that already. It's just 6 months apart. You know, if a Parkos takes a picture over here and then 6 months later take it there, and some sort of extra fancy Photoshop thing, you know, you line up as many as you can, allowing for proper motions and things, and then you can measure the motions off of that. So that's, I would assume, would be the easy part.
Do the L4, L5 of Jupiter in particular, do they kind of fluctuate in space because of the distance from the sun?
Slightly, but that's not important. It's is knowing the distance in between them, which you can get. It would take about an hour for radio signals to go back and forth, and just like measuring the distance to Venus by radar, like we were talking about last time, just send a beam out. When it comes back, a repeater, how long it takes divided by the speed of light is how far apart it is. Anybody else?
Bill,
Mm-hmm.
in doing the research for the next topic,
Mhm.
I kept running across the term vibration.
Mm-hmm.
Is that the same?
That's
I
a
want to make mention.
that's a
of
stretch use of the real word libration, so I avoided it.
I'm
But
going to make mention of it in
yeah.
particular, but I wanted you to clarify.
well,
And you can during my
libration just means nodding. So anything, whether it's the Earth turning during the night or the Moon being in an eccentric orbit around the Earth where we can see around one side or the other, or above the plane of the ecliptic so we see over the top or underneath, all of those things are called librations. And the Lagrangian points do librate or move around a little due to the eccentricities of the planet's orbits around the Sun. But that's, you know, accounted for. Yeah. Mhm. Anybody else?
Have you thought about sending a proposal to scientists?
Not sure exactly what to do on there. I have no credentials as far as that goes, being a physical biochemist and retired at that. I don't know. Right now it's just a old geezer's retirement thought. But I don't see anything wrong with it. I think it would work.
You'd have to get Albert Einstein to sign your letter.
Yeah, something like that. Mm-hmm. Yeah. Anybody else?
The cost, do you thought?
Well, they're already going to send up, the Parkes ones are old material, and the Gaias are supposedly ready to be launched this fall. So all I got to do is really make a couple of more of them. It would cost something, but depends on, you know, cost-benefit ratio. If anybody thought it was worth doing is the thing. Since we're not apparently ever going to have manned missions anymore, I think those days are over. As you know, 10 years ago, if we could get somebody up in an orbit as far as Nashville and get them back down alive, we thought that was a big deal, and now we don't even do that. We have to hitch a ride with the Russians to get to our own space station. It's, you know,
When somebody figures out how to make money in space, we're out of here.
yeah.
That's what it's going to take. Somebody figure out how to make a profit, we're gone.
It could be done.
It will.
Yeah.
Somewhere it's going.
Well, you know, if it turns out that the Trojan asteroids are made out of gold or something like that, then these are at the spot where the Trojan and Greek asteroids are, right? So while they're picking up one of those to bring back, they can leave off one of these.
Be surprised how fast the human race can get out of here. If they can.
Oh yeah, yeah. They follow the money. Okay. Anybody else? Okay. Thank you.
We'll take about a 10-minute break and reconvene for the